We did not do that today. We did that last week. Today's the 16th. I think we actually did this on the 10th. But this is the lesson we're doing today, and our goal today is to talk about 3 different types of symmetry. Did you guys know that there are 3 different types of symmetry? Most of you are probably familiar with reflection symmetry. But did you know that there's such a thing as rotation and translation symmetry also? And it's possible for something to have reflection symmetry but not have rotation symmetry, and vice versa. And translation symmetry is a really weird one that you're never going to see on a test because it's kind of like theoretical. It's not physically possible to exist. It can only exist in your brain, in your theoretical brain. But I'll show you what it looks like. But that's our goal for today. So we're going to be looking at some shapes and trying to decide, do they have reflection symmetry, yes or no? And then where are those lines of reflection? And then we'll learn what rotation symmetry is. We'll go back and look at those same shapes and say, do they have rotation symmetry, yes or no? And with rotation symmetry, we'll talk about the angle of rotational symmetry. I'll show you an example of translation symmetry, and then we will be done. So let's go ahead and get to our notes page. It's just one single page today. And to start off with, I'm going to have you guys work individually or with your table partner on this first part. I would like you to go through for each of these shapes, and if it has reflection symmetry, I would like you to draw as many lines of reflection symmetry as you can. So I will work through the first one with you, a regular hexagon. Does it have reflection symmetry? Yes, it does. Here's one line of reflection symmetry. We could fold that regular hexagon right over that line and get all the pieces of the shape to match up with each other. But that's not the only line of reflection symmetry. Can you find some more? See how many total you can find. See how many lines of reflection you can find. I see another one here. Since this has reflection symmetry, I'm going to make a note above it. I'm going to write REFL. I'm not writing R because the second thing we're going to come back after we've done this, we're going to mark ones that have rotation symmetry. And if I just had R's, then I wouldn't know if it meant rotation or reflection. And some of them are going to have both. In fact, this one does have rotation symmetry too. We'll talk about what that means in a minute. So what I'd like you guys to do right now is just focus on reflection symmetry. Go through the rest of these shapes and see if you can find any lines of reflection symmetry. If you can, draw them and write REFL over top of it. If there are no lines of reflection symmetry, just leave it blank. All right, I'm going to give you about, how long do you guys think we need for this? 5 minutes? Less? 4 minutes? Let's try 4 and see how we get. Let me know if you need any help. Rectangle had 2. These 2 had none. Regular pentagon had 5. 1 from each of the points. Did you guys get all 5 of the ones on the regular pentagon? That's only 4. There's 5. This trapezoid has none. Equilateral triangle has 3. 1 from each point. Square has 1, 2. Are there any more than 2? Diagonals work on a square. 3, 4. Isosceles right triangle has 1. Isosceles trapezoid has 1. This is an interesting one. Does a circle have reflection symmetry? I would say certainly it does. How many lines of reflection symmetry does it have? I would say there's an infinite number of lines. There are so many lines. I could draw this one. I could draw this one. I mean, there's so many different ways to cut a circle in half. So I don't think we can count how many there. A rhombus has 2. This quadrilateral has none. Isosceles triangle has 1. Parallelogram seems like it should. It seems like it has symmetry, but it does not have reflection symmetry. But remember this, we'll come back to it. It turns out a parallelogram does have this thing called rotation symmetry. All right, so let's talk about rotation symmetry. Give me a thumbs up if you're feeling pretty okay about reflection symmetry. If you were able to get most of these, maybe with 1 or 2 mistakes, give me a thumbs up if we're feeling all right about that. All right, and this is something you probably learned like way back, maybe even elementary school. I can fold this shape and it matches up onto itself so it has symmetry. Okay, it turns out there's 2 other types of symmetry. The next one we're going to talk about is rotation symmetry. This thing kind of reminds me of a fidget spinner. This thing has rotational symmetry because if you look at it right here, now I'm going to tell you to close your eyes for a second and I'll tell you when to open them. You ready? I want you to burn this image into your memory right now, okay? You got it? You got it pictured? All right, now close your eyes. Now open them. Doesn't that look exactly the same? Yes? But it's not the same. I rotated it between when your eyes were open the first time and when they were open the second time. So this is a type of symmetry not where we fold something, but where we rotate something. So if I have a picture that I can rotate and get it to look exactly the same after a rotation, then we say it has rotation symmetry, kind of. Now, we can rotate it onto itself. The point of rotation would be here. And part B says she can rotate all figures in such a way that they will not change. So Jessica is claiming that everything has rotation symmetry. Is Jessica correct? How could you rotate any figure so that it looks exactly the same as it was before? All right, so I want you to look at this quadrilateral. This does not seem like it has any kind of symmetry, but I can rotate it all the way around a full circle and it looked exactly the same as it was before. Now, technically, it meets the requirements of rotational symmetry, but would there be anything special about rotational symmetry if we allowed that? I would say no. So we really define rotational symmetry as if there's an angle less than 360 degrees, you can rotate it and get it to match up again. 360 doesn't count because technically everything would have rotational symmetry, and then it really wouldn't be anything special. There'd be no need to talk about it. So if there is an angle less than 360 that we can rotate, it has rotational symmetry. This next question I'm going to ask you is not on this sheet, and it's a bit of a stretch. This is an advanced question, so I hope that you all give it a thought here. This is not one of our key learnings today, but a little bit extra that'll come up later on. We also talk about an angle of rotational symmetry, and it is the smallest angle that you could rotate something and get it to match up onto itself. If you are up for it, would you please find me the angle that you would need to rotate this in order to get it to match up on itself? The smallest angle. Don't say it out loud. Write it down right next to this shape if you're up for it. How many degrees would I need to rotate this thing to get it to match up onto itself? Now you could do it 360, but see if you can find a smaller angle. See if you can find me the smallest angle that you could rotate it and get it to match up. I'm just curious to see what you guys come up with. We got some really interesting answers yesterday. I want to show you guys my favorite wrong answer to this. And I actually didn't get any of these today, but I usually see this one. And maybe some of you were thinking about this. Now this isn't right, but I love this answer because it's wrong, but it's on the right track. So was anybody thinking 33.3 degrees? Nobody in here had that thought today. I'm going to show you how people usually get 33.3 degrees. They do 100 and they divide it by 3. Now, can you see in this shape why they would divide it by 3? Because there's kind of 3 things there. There's 3 spokes to it. And this divide by 3 thing is really on track. For those of you who got the correct answer, what one small change would they need to make to their calculation here to arrive at the correct answer? Well, there's only one small number they need to change here. What would it need to be? Yeah. If they had used 360 instead, they would have come up with the correct answer, which was 120 degrees. So to rotate this thing all the way around, you'd have to go 360. But you don't need to go all the way around. You only need to go 1/3 of the way around to get it to match up. How do I know it's 1/3? Because there's 3 spokes there. Okay. So if you're not comfortable with that, that's not a big deal. What I want you guys to do right now is go back up to the top, and we're going to go through and we're going to make a note of any that have rotational symmetry. And if you're up for the challenge, see if you can find the angle of rotational symmetry. So this one right here, I would say does have rotational symmetry because notice how it's flat on top. If I turn it like that, it's flat on top again. Okay, and I did not turn it 360 degrees. I only turned it a little bit. So I'm going to say rotational symmetry here. A kite, I don't think I can make a kite look the same way by turning it unless I go all the way around. So that does not have rotational symmetry. See if you can just make a note of which ones have rotational symmetry there. I'm only going to give you about a minute for this because this tends to go pretty quick. If you get finished early, see if you can figure out what the angle of rotational symmetry is. And then we're going to come back and talk about our last form of symmetry. Just one more minute. We'll talk about rotational symmetry, and then we'll go on to our last form. So, well, I'm going to go ahead and get started here. I'm going to mark the ones that I think have rotational symmetry. And for those interested, I'll give the angles also. This has rotational symmetry with an angle of 60 degrees. Rotational 180 degrees. This angle thing is not something I'm not going to be testing you on. So if you didn't even attempt that, that's fine. Rotational, I want to say 72 degrees. I could be wrong there. Rotational 120. Rotational 90. No rotational, no rotational. Ooh, this one's a weird one. Do you think a circle has rotational symmetry? What would the angle of rotational symmetry be? I don't think we can say because there is no smallest angle, right? Give me the smallest angle you think of, and I can give you a smaller one. 1 degree. Mine's a 1/2 degree. You go with a 1/4 degree. I'm going with a 1/10 of a degree. A 40th. We can go forever, right? So you can always get a little bit smaller. So I think it does have rotational symmetry, but we can't really talk about what the angle is. This rhombus would have rotational symmetry with 180 degree. No, and it turns out the parallelogram does have rotational symmetry 180 degrees. Now a lot of you were thinking that this had reflection symmetry, and when you look at a parallelogram, there is something that seems symmetric about it. It has rotational symmetry. Where's the pass? Oh, okay. Gotcha. Okay, any questions about rotational symmetry? How are you guys feeling right now? If I put a shape in front of you, could you look at it and say yes or no, this has rotational symmetry or not? Give me a thumbs up if you're feeling all right about that. All right, this last thing, I want to show it to you. I want you to see it, but it's not something I can really test you on because it doesn't actually exist in the real world. I'm going to show you an approximation of what translation symmetry looks like. And it looks something like this. Now the reason I would say that this has translation symmetry is if you keep your eye on, where is it? This fish right here. If I translate this thing over just enough, there's another fish right there that resembles it. Now, in order for this thing to actually have translational symmetry, though, we could not have an edge to this. It would always, no matter how far I moved it, you should be seeing the exact same thing, which means the only way for this to have translational symmetry is if it were infinite, and this pattern went on forever and ever and ever, and both up and down and left and right, which is not physically possible, right? So the idea of translational symmetry is not physically possible, but we can approximate it. So anytime you have a two-dimensional pattern, that would have translational symmetry. This is one that we're actually going to do in class later on this year. Certain days, like those half days before Thanksgiving or the day before winter break, we'll often do what I call arts and graphs, where we'll make something that looks cool using geometric properties. We'll break out the compasses and the straight edges, and so this is one of the constructions that we'll do. And you can copy it and make it into tiles. By the way, does anybody know what this is called? It starts with a T. When you make a pattern that goes on infinitely and kind of repeats itself over and over again. It's called a tessellation. Have you ever heard that word before? That's what a translational symmetry looks like, but I won't be testing you on it because we can't actually achieve it in the real world. Okay, that's what I got for you guys for today. If